Oh, hey, Physics 30s, it's me, Mr. Jukely again. We are today on Unit 6, Lesson 2, still in nuclear physics, which is pretty cool. We're doing decay reactions. You'll notice that it used to say day 1 here, but I kind of got rid of that and scribbled it out a little bit. It's a little bit longer of a lesson. I used to typically teach this one in about a day and a half. So that being said, it's probably going to be a little bit longer of a video. So if you need to put it on pause somewhere, take a break, come back to it, that's totally cool. But I will try and make it fairly quick for you. One thing that I'll note with this, there's this video called Twisting the Dragon's Tail. I'm not sure if this YouTube link works anymore, and it's not something I'm actually going to show you because it's an hour and a half, but it fits in very, very, very well with our Unit 6. Twisting the Dragon's Tail is the name of it. It's the guy from Veritasium who's done like a feature-length documentary. Check it out if you want to, if you need something to do. But anyways, yeah, let's jump into this. So when we talk about decay, we typically talk about decay and the radiation that's given off of it. In 1896, Henry Becquerel accidentally discovered that the uranium exposed photographic film. The story goes that he had some film stored in a tin, because way back when it was stored in tins, and he had it in his desk, and he threw the film, the unexposed film, into his desk, and threw some uranium in with it and pulled it out the next day, and it was exposed as if it was exposed to light, which is kind of weird. So then Henry Becquerel, who is also, by the way, kind of an accidental physicist is what I've read. He was an engineer, and his father was the head of physics at some university, I forget which one, and when his father died, he took over the role, which is kind of interesting. But anyways, I'm rambling, so we should move on a little bit. So since then, scientists discovered that there are typically 3 types of radiation that are emitted from these nuclear decay equations. I should also, I guess, mention the nuclear decay equation is when the nucleus changes. So we'll talk about that as we go through. So there's alpha, beta, and gamma radiation. And we already, from this diagram, have kind of an idea about penetrating ability. So how well they penetrate things. So if you had to rank these from the best at penetrating to the worst at penetrating, what do you think you'd have? So the best penetrator, gamma. Look, it goes straight through paper, goes through wood, only really stopped by like thick concrete and lead and stuff like that. Then we've got beta radiation. It goes through paper, no problem, but oh, look at that, blocked by wood. And then alpha doesn't even make it through paper. So we should have an idea about the penetrating ability of those 3 things. We should also have an idea about the ionizing ability. So when we call it an ionizer, we're talking about like how easily it can ionize other things. And when it comes to us, it's how dangerous it is to us, because if something can ionize things inside of our cells, well, that's horrible for us, right? Absolutely horrible for us. So we really don't want that. So the best ionizers, or the strongest ionizers, are alpha particles. They are particularly dangerous to us when they are inside of our body. All right, so they can ionize a lot of those sensitive things. Things don't like being ionized. They're essentially destroying cells inside of our body and destroying this DNA inside of cells inside of our body. Which to a liver, a appendix, a pancreas, your brain, any of those things can do some serious damage. That being said, they're not a huge danger outside of our body because they're blocked by the outside layers of our skin. They're not very good penetrators. Great ionizers, but not good penetrators. On the other side of the spectrum, we've got gamma radiation. So our gamma, which is a photon, as you recall from other sections of this course, they are the best at penetrating, but they are the weakest ionizers. So a lot of the gamma rays pass straight through your body. That being said, they can ionize. Typically most dangerous when they're outside of the body and when they're in high doses. So the most opportunity to interact with your cells and ionize your cells. What we didn't talk about there was beta radiation. Beta's kind of in the middle, right? So we talked about one extreme, we talked about the other. Beta's in the middle of those two. Okay, separating radiation. So in order to separate radiation, we kind of need to know more specifics about what those types of radiation are. So we talked about gamma radiation. The symbol for gamma radiation is going to look like this. That is legitimately just EMR. It's very, very high energy, high frequency EMR, but it's EMR. Then we've got alpha particles. The symbol for an alpha particle looks like this. And what we know is alpha particles, and I think we've mentioned this before, they are helium nuclei. So alpha particles are helium nuclei. They do have a charge, and they're pretty big, right? They're 2 protons, 2 neutrons. Okay, and then the last one is a beta particle. The beta particle, the symbol looks like this, and there's actually 2 types. There's beta positive and they're beta negative. We'll focus on beta negative for now. So if it's negative, it's actually just an electron. So negative is an electron. Positive is called a positron. Again, we'll talk about that a little bit later. So separating these 3 types of radiation. Okay, I've got an external magnetic field. I've got a radioactive source that gives off all 3 types. Could we figure out what they would look like as they go through those that field, that magnetic field? So I'm going to do something very, very, very specific here. Let's see. So first off, I need to get out a picture of my hand rules. Alrighty, so I got out my couple hand rules here. Took me a second to find them, not in your perspective, but in mine. I got my right hand rule number 3 and my left hand rule number 3. We're gonna need both right and left because we've got positives and negatives. So let's start with the helium nuclei. So for helium nuclei, it's a positive. So I think I'm gonna want my right hand rule number 3. So when I look at my right hand rule number 3, my fingers have to be pointed in the page. So you see in the picture, my fingers are pointed in the page because my fingers are the magnetic field. Perfect. The velocity of the alpha particle is towards the right. So I need my thumb to be pointed towards the right. And then remember, my palm is the way that the magnetic force is. It's the way that the alpha particle is going to be initially directed. And let's see, I'm going to do something again very specific here. Get a real fat marker for this. And the alpha particle, okay, alpha particle, I'm going to put in blue, is going to be deflected up something like that. Any ideas why I drew it as a big fat line? The big fat particle, right? It's a 2 protons, 2 neutrons. It's an alpha particle. It's way bigger than an electron. Way bigger than an electron. Okay, cool. So we've got the alpha particle. For the beta radiation, or for the electron, I want my left-hand rule. So I've got my left-hand rule right here, spinning around all fancy. Again, fingers have to be pointed into the page. My thumb has to be pointed towards the right. The only way that my palm can face in this case is downwards. That's my magnetic force. Again, I'm going to do something very specific here. I'm going to have it a much smaller line, but also a much smaller radius as well. So the radius of curvature is significantly smaller. And I kind of have it like swirling into the center. We'll talk about that a little bit more, spiraling into the center. But could we take a hot second here, and could we think about why the radius would be smaller for the alpha particle, assuming that they're similar speeds? So what type of motion does it get into? Oh, and I should put this as my beta negative. I'll even put it like that for now, so we know it's negative. So Fc is equal to Fm. We can expand on this. mv squared over r is equal to qvb. We see one of the velocities cancel. And again, assuming that they're at relatively similar speeds, the charges are pretty equal as well. We got -1 versus +2, so not huge. It's the mass that's different. It's like tens of thousands of times bigger in terms of mass. So when I look at the relationship between mass and radius, it turns out to be a direct relationship between mass and radius. So the bigger the mass, the bigger the radius. So cool. Okay, last one. We actually haven't talked about all of them yet. Okay, I need a very specific felt pen for this one as well. I think I have it in red there. Perfect. So the gamma radiation. Is it deflected by a magnetic field? No. So gamma radiation goes there. Cool. Okay, I guess I'm kind of going all over the place here. But do you remember nuclear notation? Might as well start talking about that here. Nuclear notation. So if I have my beta particle kind of looking like that, the top number is the mass number. The bottom number is the charge. So if I'm talking about a beta particle, right? Does it have mass really compared to the other things like an electron? Remember, we're talking tens of thousands of times less. It's like you pick up a paperclip, you put it down. Yeah, I mean, you kind of change the mass a little bit, but the paperclip's so small, it realistically doesn't change your mass. That's like an electron. It's so small, right? Whereas an alpha particle, I might as well write this out as well, an alpha particle has a very significant mass. It's got 4 nucleons in total, and it's got a charge of +2. So this would be our nuclear notation for an alpha particle. Might as well do a gamma while we're at it as well. 0 mass and 0 charge. Cool. Okay. Going a little out of order, but that's fine. Hey, can you think of a different way that you could separate these 3 types of radiation? Probably, because it's on the screen right now. We've got parallel plates, right? So we can deflect them with parallel plates. I think I was using blue, a great big fat blue for my alpha particle. So things that I'd want to think about here is, well, which plate is positive and which plate is negative. I'm going to switch back to black. The top plate is positive. The bottom plate is negative. So which way would an alpha particle be deflected here? An alpha particle, back to a big fat blue marker. Okay, eventually alpha particle would be deflected towards the bottom plate. So alpha particle, holy moly, towards the bottom plate. Where would a beta or an electron go? Towards the, I think I was using green for it. So towards the top plate, still with a smaller radius, although I don't know if we'd really call it radius because now this is parabolic motion. And what about gamma radiation? Gamma radiation just passes straight on through. Oh, I didn't mention why we're using a dotted line for gamma radiation. That actually comes up with something a little bit later on in the course in terms of our particle tracks. So when we're actually making particle tracks, an alpha particle will make a big fat track, a beta will make a skinny little track, and gamma will make no track whatsoever. So we typically put it as a dotted line. Cool. Okay, I'm rambling a little bit here. Sorry for that, folks. So one application of this is food irradiation. So essentially what they do is they zap the bacteria, they ionize the bacteria, and that kills the bacteria, which is what we don't want in our skin, but we are in our bodies, but we do want in bacteria. So here is a really old picture about irradiated strawberries. So this is 25 days. Let me go back to my original marker here. This is 25 days after treatment in storage at 3 degrees, so essentially in a fridge. And we see with no radiation, they're kind of moldy. You wouldn't eat that. With a bit of radiation, looking pretty good. You might pick around, might eat still some of it. With a decent chunk of radiation, looks delicious, right? So this is one way between this and the fridge. 2 ways, realistically, that we make food last longer and longer and longer. One issue with this is people don't necessarily like it. It's usually people who don't necessarily understand it that don't like it. You know, they say, okay, well, you're eating radioactive food. You're not really eating radioactive food, right? You're eating food that's been irradiated, which means it's killed the bacteria, which means it's probably going to last longer and potentially be better for you. I don't know if I should say better for you, but will last longer. So yeah, there's lots of issues like that with people that don't understand. Anyways, our decay equations. There are 3 types of decay that we need to know about, 3 types of equations that we need to be able to go through. And we already know, so there's alpha decay, beta decay, and gamma decay. Alpha obviously gives off alpha particles, beta gives off beta positive particles, sorry, but they could be positive or negative, and then gamma gives off gamma radiation. So we'll talk about each of those in turn. First type, alpha decay. So alpha decay is typically when there's too many protons in the nucleus, and we know if there's too many protons in the nucleus, we know that positives don't like being next to positives, so there's a very strong electric force that's trying to separate those two. We also know that there's a nuclear strong force, but the nuclear strong force only really works on very, very, very extremely short distances. So if the nucleus gets too big with too many positives, well, the nuclear strong force can't work from one side to the other, and the nucleus will want to break apart and get rid of some of those positives, get rid of some of those protons. Too many protons for the nucleus to be stable. I should also, I suppose, mention with this, we're changing things a little bit here. In Science 10, Chem 20, Chem 30, all those different courses that you've been in before, you say that you cannot change the number of protons inside of a nucleus. It's true to an extent. You cannot change the number of protons in a nucleus unless you change the type of nucleus. So for example, carbon, very common isotope of carbon, is carbon-12. So carbon always, always, always has 6 protons. No matter what has 6 protons. If you were to change that by even 1 proton, it would no longer be carbon. It would be something totally different with totally different properties. So if you change the number of protons in a nucleus, you're totally changing what type of nucleus you've got. Okay, so let's check this out. Consider the alpha decay of radon-222. Okay, so what I want to do is I want to make a balanced decay equation for this. So I got to go through, and there's actually 2 new physics principles that we need to deal with for this one. So let's go through and let's check it out. I've got radon, Rn, it's 222, and we have to figure out what its atomic number is. So I go on to here, and we're trying to find radon. I think it might actually be in an area that I can't see. Ah, yeah, there it is. There it is right there. Number 86. Perfect. Okay, so we've got that. How do I go back to my original sheet here? Get that. Radon, I think I said 86. Good. We know if it's alpha decay, it's going to give off an alpha particle. And I know that an alpha particle is just a helium nuclei, so there are 4 nucleons in total, 2 of which are protons. And then the thing that I'm looking at here, if I want the complete balanced thing, I want to figure out what the other nuclei is, what the other thing is. So I'm just going to put a question mark for there. Now a couple of things that we, new definitions. What you're starting with is called a parent nuclei, and what you end up with is called a daughter nuclei. And then obviously the alpha is your radiation. So don't ask me where those come from. I do not know, but parent and daughter, I mean, like I have an idea, but why they, anyways, whatever. Cool. Okay, so we have to figure out what that question mark is. So the 2 new-ish physics principles that we have to deal with here. If we look at our yellow data sheets, we've got conservation of charge. So where am I gonna write this? Physics principle 7 is conservation of charge, and we've got physics principle 8, which is conservation of nucleons. I'm just gonna write that out. Charge, nucleons. Perfect. And we know what conservation means. It means essentially keeping the same. So we have to have the same charge before and after. We have to have the same number of nucleons before and after. Perfect. So physics principle 7, all about charge. These are our bottom numbers. Bottom numbers. And conservation of nucleons, when we're looking at our individual elements or nuclei, I guess, these are our top numbers. Cool. Okay, so now we can figure this out because we know it's got to be the same before and after. So before, I have 222 nucleons. After, I need 222 nucleons. So I've got 4 of them taken up for my alpha particle. That means that there must be 218 in whatever that question mark is, because 218 plus 4 is 222. So conservation of nucleons, check. Physics principle 7 is all about conservation of charge. So I've got 86 positives on the, I don't really want to call it a reactant side, but on my starting side, I need 86 on the other side. So 2 of them are taken up. I think this has to be 84. And as soon as I figure out that it is 84, so just remember that 218 and 84, 218 and 84. As soon as I figure out it's 84 protons, I can identify it because it's kind of like the ID number. So 84, hey, look at that, it's polonium. PO. So let's go back here. Let's call this PO. Sometimes the question might ask to like say what it is. So we'll just say polonium-218. Cool. We figured out what the daughter nuclei is. Conservation of charge, conservation of nucleons. Excellent. Okay. So another new definition here. Because the type of nucleus has changed, anytime the type of nucleus has changed, we're going to call that a transmutation reaction. So transmutation reaction, that is something to know anytime the nucleus changes. Cool. So gamma radiation I like to think about this as the little brother that tags along sometimes. So we've got the parent nuclei, we've got the daughter nuclei, and then the little brother that sometimes tags along, little brother. Cool. Think about how this works. There's tons and tons of energy that's typically given off with these decay equations, right? Alpha and beta decay. So sometimes what happens is that the daughter nucleus is left in an excited state. So it's got high vibrational energy. It's left in an excited state. It wants to go to it down to its nuclear ground state. As it falls down to its nuclear ground state, you'll never guess what it's going to give off. Are gamma radiation. So that doesn't happen all the time with every single nucleus no matter what, but it does happen with some of the nucleus. Please keep in mind that when we're talking about this, we're actually talking about, you know, like a chunk of material, like a decent number, where we rarely ever see one individual nuclei is what I'm trying to say. Okay, so in addition to physics principle 7 and 8, there are two other conservation laws that we need to be able to apply to this. So two other conservation laws. Any ideas what they could be? So one idea is this is essentially like a little explosion, right? Where I've got my big nucleus, it explodes into two pieces, a smaller alpha particle and a slightly smaller second nucleus. Explosions, hey, that takes us back to Unit 1. If you are thinking to yourself, physics principle 4, our conservation of momentum, perfect, you are spot on with this. So our total momentum before is equal to our total momentum after, most excellent. Now when we think about this, we're going to assume a lot of times with this that our parent nucleus is at rest. So how much momentum do we have before if our parent nucleus is at rest? Got nothing, right? 0 before, if it's at rest. And then after, that's going to be equal to the momentum of the alpha particle plus the momentum of the polonium. So if the parent nuclei is at rest, if parent at rest, the momentum of the alpha particle must be equal to the momentum of the polonium, but in the opposite direction. Excellent. Now that makes it real easy for us because that's always going to be a 1D. It doesn't matter if it's like exploding off at angles like this. We can say it's all in that one plane, so it's all going to cancel each other perfectly. So it's a 1D situation no matter what. Awesome. Okay. The second physics principle that we need to look at, or fourth, depending on how you're checking this out, is our conservation of mass energy. So physics principle 6, where I've got my mass energy before must be equal to my mass energy after, my total mass energy after. So thinking on this one, if the radon is at rest, what type of energy would it have? So at rest, it can't have kinetic, gravitational, no, out of the question, spring, out of the question, nuclear potential, I guess you could kind of call it that, but where does that energy in the nucleus come from? Well, it actually comes from the mass defect. Delta mc squared is where all of that energy is starting off. And then what's it going to turn into? So it's going to turn into the kinetic energy of the alpha particle plus the kinetic energy of the, in this case, polonium. I'm going to put after for both of those. And then I'm going to put in brackets, if you have a gamma photon, you can have the energy of that photon after as well. And we remember how to calculate kinetic energy, no problem, 0.5 mv squared, photon energy, HF or HC over lambda, delta mc squared. The biggest part of this is the delta m, so that's the mass, well, let's do mass final minus mass initial in absolute brackets is a real easy way to look at it. So that's the mass, the total mass of the products minus the total mass of all the reactants, which can be a pretty big calculation. Okay, anyways, I kind of just wrote it out for those. Let's check out a quick example and let's see what we can do with this. We have a parent nucleus that is at rest, perfect, undergoes alpha decay. tells us the daughter nucleus is francium-223, and then tells us the actual atomic mass in atomic mass units. The alpha particle is emitted at 5.8 times 10 to the power of 6 meters per second. First and foremost, we want to identify the parent nucleus. We can do that. So just have to set it up a little bit backwards. We know that an alpha particle is being given off. Put the 2 in the wrong place, but that's okay, easy to fix. An alpha particle has 4 nucleons and 2 protons, 2 of which are protons. Cool. We know that francium is the daughter nucleus, so Fr, it's 223. I have no idea off the top of my head what the atomic number of that is, so let's go back to our periodic table. Let's just get rid of this stuff. Francium, Fr, where are you, where are you, where are you? It is number, not on this screen. There it is, 87, 87. There, that's an eraser. 87, okay, perfect. Let's go back over here, lots of flipping around. 87. Okay, so I'm dealing with physics principle, let's see, 8 for the top, physics principle 7 for the bottom, so law of conservation of nucleons. I got 4 nucleons plus 223 must be 227 nucleons. Cool, okay. Next, I've got 87 protons plus 2 protons. Oh, that's 89 protons. Even I can do this math in my head. So what has 89 protons? Let's see, let's see. Oh, there it is. Actinium, 89 protons. Actinium. So AC, and then if we wanted to identify it, we could just put actinium-227. Cool, we now know what the parent nuclei is. That's not so bad. Part B, determine the recoil velocity of the daughter nucleus, and we want to state any assumptions. So recoil velocity of the daughter nucleus, stating any assumptions. So right off the bat here, right off the bat, recoil velocity, that reminds me of Unit 1. So my guess is with this, I'm going to be looking at physics principle 4, conservation momentum. Let's see if we can get that working for us. So conservation momentum says total momentum before is equal to total momentum after. Oops, after. Put the after in a bad spot. There we go. So back to the original question, I just want to check something. So perfect, it is at rest. So the parent nucleus is at rest. That means we don't really have anything from before. And then after, I've got my momentum of the alpha particle plus the momentum of the actinium, I think, AC. Awesome. So we're looking for the recoil velocity of the daughter nucleus. So recoil velocity of the daughter nucleus, I'm going to go ahead and solve for PAC. That's going to be equal to the momentum of the alpha particle, but in the opposite direction. That's why we have the negative there. It's in the opposite direction. Cool. Okay, good stuff. Let's expand this out a little bit. MV is equal to MV. I'm going to be very specific here, just so I don't get things confused. And the recoil velocity of the daughter nucleus, well, there we go, must be equal to the mass of the alpha particle times the speed of the alpha particle divided by the mass of the actinium. Cool, okay. Probably start to plug a few things in here, I bet. So the mass of the alpha particle, I'm just going to get that straight off my data sheet, to be honest. So alpha particle, let's see, 6.65 times 10 to the power of negative 27 kilograms. The velocity of the alpha particle is given to me in the question, so 5.8 times 10 to the power of 6 meters per second, and then divide that by the mass of my actinium. Hold on, did I make a screw up here? Oh no, the daughter nucleus, not actinium. Oh geez, I did make a bit of a screw up, but it's not a super bad one. It's not the worst one I've ever made in class, so that's good. So it's not the actinium that we're looking for, it's the francium. MFR, that was the parent nucleus, is the actinium times the velocity of francium, and so divide by mass of francium. Okay, this makes way more sense. Way more sense. Okay, So here's what I've got. Okay, so I've got my actual mass of that nuclei being 223.0197 atomic mass units. Oh, I can't put atomic mass units into this. I'm just going to do a bit of an aside over here and say 223.0197 atomic mass units. And then, you know what? I'm putting myself in a corner, so I'm going to do that same thing, but down a little bit further. So the mass of the francium is 223.0197 atomic mass units. I want to go ahead and multiply that by, let's see, it is 1.66 times 10 to the negative 27 kilograms for every 1 atomic mass unit. Awesome. Okay, let's plug that in. Let's go ahead and plug that in. So the mass of the francium, I'm ending up with 3.702 times 10 to the power of negative 25 kilograms. Okay, there we go. Now I think we're ready to plug that in. 3.702 times 10 to the negative 25 kilograms. So take a moment, plug that into our calculator. I apologize, this is messy. This is quite messy. The velocity of the francium after. Plug it in, I end up with 1.04 times 10 to the power of 5 meters per second. Now, I didn't take into account the direction. I kind of left that negative out there. So if you left that in, you'd end up negative, which just means opposite to alpha particle. So I'll leave that as opposite to alpha particle there. Cool. Okay. So barring some major screw-ups on my part and some poor planning, I think we got there, right? Conservation of momentum. Oh, and I have everything all written out for me. Okay, so that's interesting. Okay, determine the mass defect is the third part of this. So the mass defect, the only place where we really see our mass defect is our conservation of mass energy. So that's physics principle 6. Our mass energy before must be equal to our total mass energy after. So when I expand on this, I've got delta mc squared. It's going to be equal to my kinetic energy of the alpha particle plus my kinetic energy of the francium, so Fr, afterwards. So both after. Nice. This isn't too bad, right? Like all I'm really doing is solving for the mass, or the mass defect, so I just divide both sides by c squared. Nice. We can do this. Okay, so delta m, I'm just going to expand on a couple things. My kinetic energy of the alpha particle is 0.5 times the mass times the speed squared of the alpha particle, of course, plus my kinetic energy of francium, so 0.5 times the mass of the francium times the speed of the francium squared, and then all divided by the speed of light squared. Cool, that's really not so bad. Okay, so 0.5 times 6.65 times 10 to the negative 27, just our regular mass of an alpha particle straight off our data sheet, times the speed, I believe it was 5.8 times 10 to the power of 6 meters per second. Don't forget to square that one. We're going to add to that 0.5 times the mass of the francium. We figured that out. I thought I had it up here somewhere. There it is. 3.702 times 10 to the negative 25 kilograms. And then the speed of the francium, well, hey, we just figured that one out, didn't we? 1.0418. Notice I'm not rounding it here. Times 10 to the power of 5 meters per second. And then again, don't forget to square that one. And then this whole entire gigantic thing is divided by 3 times 10 to the power of 8 meters per second. And one more time, don't forget to square that one. Cool, so take a moment. You might want to even put it on pause for this one, but take a moment, plug in some numbers. I'm doing the same thing. Alrighty, so I'm ending up with 1.27 times 10 to the power of negative 30 kilograms. All right, that is my mass defect or the difference in mass between the products and the reactants of this equation. Cool. That doesn't seem like a lot of mass. And if we were to use the energy for that, so delta mc squared, to figure out the actual energy, it wouldn't seem like a ton of energy. But remember, that's actually a fairly big amount of energy for one individual nuclei. If you have millions or billions or trillions or a mole of those, you're going to have a lot of energy being given off. There's so much energy stored in the nuclei of atoms. Oh, space to work. Excellent, excellent. Okay. Next one that I want to talk about, and this is where I typically split it apart into like one class and two class, so this might be a place for you to take a break if you need one. And let's see, you might want to write down the time. It's 35, holy mackerel, 35 minutes already. Sorry about that, folks. I know it's a long one. We'll try and go quick. Beta negative decay. So when the nucleus has too many neutrons, it also becomes unstable. There's lots of things that can make it unstable. This is due to the nuclear weak force. The nuclear weak force is a difficult force to describe because it's not really so much in terms of pushes or pulls. It's more in terms of like telling what subatomic particles, like what they are. So keep that in mind. Try not to think about it in terms of push or pull. Try and think about it in terms of telling you what things are. Okay. So let's consider the beta negative decay of sodium-24. Beta negative. That means we're giving off an electron. So I've got my sodium-24, 11 protons, 24 nucleons in total. It gives off a beta particle, which remember is just an electron, so essentially zero mass with a charge of -1. And look at this, it gives off apparently magnesium-24, Mg. So let's think about this for a split second. The top numbers, we're dealing with physics principle 8, the conservation of nucleons. Does the conservation of nucleons in my reactants match the products, 24 and 24? Absolutely. What about the charge? So I've got 11 positives on this side, and then on this side I've got -1 plus 12. That's still 11 positives. So those same laws apply, right? Physics principle 7, physics principle 8. Now, there's a bit of an issue because the other two conservation laws, conservation momentum and conservation mass energy, they didn't actually balance the way that this is written out. Some energy and some momentum is missing. So it's actually Wolfgang Pauli in 1930 who proposed a new type of particle that accounts for that missing energy and momentum. It essentially has no mass, it has no charge, but it does have energy and momentum. Now that being said, it essentially has no mass. It has a tiny kind of bit of weird mass, but more on that in other physics courses. So more specifically, for beta negative, it is an antineutrino. Notice no charge, no mass as far as things are considered here, and it is anti. Anytime you see anti, you typically put a negative, or sorry, not a negative, a line on top. So it's an antineutrino. So Wolfgang Pauli did this. Problem was they were so difficult to figure out, these neutrinos and antineutrinos. They're so small, they're so unreactive that they can actually pass through the entire Earth without interacting with anything. They're passing through you right now too, which is weird, right? Like, who knew? There's these tiny subatomic particles that are passing through you, they're passing through the entire planet. That being said, not all of them pass through the entire planet without interacting with things. Some of them definitely do, but they can pass through the planet. So, if you're looking for an interesting thing, check out neutrino detectors. You can just go on YouTube and check it out. There's an episode of The Newer Cosmos with Neil deGrasse Tyson where he actually goes into, this is the, I forget the name of it. This is the one in Japan, the neutrino detector, and it's pretty cool. Essentially what we have is heavy water here. Heavy water has deuterium or hydrogen-2 in it. The neutrinos interact with that causes a bit of a chain reaction and then eventually gives off light. All of these golden globes up here, not the awards, but actual golden globes in this case, are very, very, very sensitive photon detectors. So when they give off light, when they interact with the heavy water, they give off a little tiny bit of light and then they're detected there. These are typically buried like deep, deep, deep underground so that other things don't mess with them, other subatomic particles. It's pretty cool. Okay, so we talked about antineutrinos. It turns out they're an antiparticle, and every particle that we know has a corresponding antiparticle that has an opposite charge or other more advanced properties that we'll talk about a little bit later. So for an electron, it's got a fancy name, a positron. You could call it an anti-electron as well, but it's a positron. For a proton, no fancy name. It's just an anti-proton. Guess what the charge would be? Positive, a proton with a negative charge. Weird, right? A neutron is just an anti-neutron. Still just a symbol N. That's one where some of the intrinsic properties are a little bit different. And then a neutrino, anti-neutrino. Oh, and I forgot. So you can put a little line over top so you know the difference. So neutrino versus anti-neutrino with a line over top. Cool. Okay. One interesting thing that happens with particles and antiparticles is when they collide, they don't bump into each other. Nope, they do something way more interesting. They completely 100% annihilate each other. They destroy each other, and all that's left over is gamma photons. So no more matter anymore whatsoever. Pretty wild. And this happens with any pair. So like an electron and a positron, a proton and an antiproton, a neutron and an antineutron. They come in contact, kablamo, they're gone. Which is pretty wild. We'll talk about that more a little bit later. We'll do a bit of math with that in another lesson. Okay, type 2b, beta positive decay. This is a second type of decay where a proton turns into a neutron. So this is again due to the weak nuclear force. So too many protons, one turns into a neutron. I kind of forgot to mention that in the last one, but let's check out the beta positive decay of oxygen 15. So beta positive, we give off a positron. Charge of +1, mass of 0. Cool. Oxygen 15, okay, so if I got 15 nucleons over here, I need 15 nucleons over here. So physics principle 8 checks out. Physics principle 7, let's see, physics principle 7 for those bottom numbers, I've got 8 positives on this side, I've got 1 + 7, 8 positives on this side, so physics principle 7 checks out. We need to, and you absolutely have to include a regular neutrino, not an anti-neutrino, a regular neutrino with this beta positive decay. So beta negative, you get an anti-neutrino. Beta positive, you get a regular neutrino. Cool. Okay, there it is. So one application of this is PET scans. PET scans stands for positron emission topography. So essentially they inject the person with positrons. The positrons smash into your electrons and they give off radiation, and then they can tell exactly where they're smashing in. Great for soft tissues. So this is like brain activities for normal people, mild cognitive impairment, and people with Alzheimer's disease. Okay, so quick summary of this. Beta negative gives off an electron and an antineutrino. Beta positive, an anti-electron or positron, and a regular neutrino, just to sum up. Alrighty, we've got 3 last quick examples. There's not really a ton of math involved with these ones. I'm going to get you to put your video on pause and try these 3 out. So put it on pause 2, 3, 5 minutes, whatever it takes, and try these ones out. I'll unpause, we'll walk through it, we'll figure it out. Go for it right now. Alrighty, so let's go through and let's check this out. So all it is really figuring out these decay equations, right? So I got indium 115. So indium 115. I need to know exactly what indium is. So let's see. I think it is 49 protons, and it says it goes through beta negative decay. So right off the bat, I know I've got a beta particle. It's beta negative, so 0 mass and a charge of -1. What is the daughter nuclei? So we're looking for this daughter. I like to put a question mark there just as a placeholder. Let's go through and do the math. I've got on the top, physics principle 8, 115 nucleons. I need, you got it, 115 nucleons. On the bottom, physics principle 7, conservation of charge. I got 49 positives. I need 49 positives, so that means it must have 50 protons for whatever the heck this one is. So what exactly has 50 protons? Oh, tin has 50 protons. Let me get back to my thing here. So tin is SN. And now you might be thinking to yourself, okay, I'm done. Are you really done? No, because beta negative, we need to know it includes our anti-neutrino, and then sometimes, so sometimes, you can put this in brackets, you need it if the question tells you that it includes gamma radiation. Otherwise, safe bet to just put in brackets off to the side. The little brother that tags along with the daughter nucleus, sometimes gamma radiation. Cool. Now I think we're done. And we know that we have tin 115 as our daughter nucleus. Cool. Okay. Sounds good. Sounds good. Yeah, the one thing that I guess I should mention with this is the mass didn't change, so we still have the total number of nucleons that is exactly the same, but one of our neutrons must have turned into a proton. So we have 49 protons to start, we have 50 protons to finish. So if the mass number doesn't change, it's just one of the neutrons turned into a proton. Okay, part B, we've got nobelium-255 decays into which isotope of fermium? Okay, so nobelium, that's NO255. I got to look up real quickly the atomic number of nobelium. I believe it is 102. And this is telling us that it is decaying into fermium, so that's Fm. And the thing that I know about fermium, right off my periodic table, is it's got an atomic mass of 100. Cool. So now with this one, we're working a little bit backwards. So we're saying, okay, well, what type of decay could this go to? So I'm going from 102 protons to 100 protons. That means that whatever this thing is must have 2 extra protons. Hey, that's an alpha particle if I ever heard of one. Alpha particle is 2 protons. Nice. Okay. Now I just got to deal with my conservation of nucleons. So 255 minus 4, I think this should be 251. So it decays into fermium 251. Excellent. And remember, sometimes you get that gamma. Cool. Okay, last one to check out here. Beta positive decay. The daughter nucleus is nitrogen 11. What the heck is the parent? Okay, so in this case, the daughter nucleus is nitrogen, 11. So nitrogen, this is one of the few ones that I've memorized. Nitrogen has atomic number of 7. It's saying that it's going through beta positive decay. So beta positive, so notice the +1 there. We know if it's beta positive, I might as well just fill this in right here. We know if it's beta positive, it's going to give off a neutrino. And then, of course, sometimes our gamma. Sometimes. All right. So I got everything filled out that I know about. Now let's go through and look at the piece that I don't know about. So whatever this question mark is on this side, I know it's going to have 11 nucleons because the product side is 11 nucleons. Cool. Let's see. I've got 7 plus 1 positives on this side, so I need 7 plus 1. I need 8 positives on this side. Cool, I can get rid of that question mark because I know what has 8 protons. It's oxygen. So the parent nucleus is oxygen 11. Cool. All right, folks, I know that this is a bit of a longer lesson. I'm proud of you for sticking with it. I'm proud of you for sticking with physics and working your way through everything. I hope you all know that. Do a bit of practice. Let me know how things go, and we will chat again soon. Okay, that is it for now, everybody. Where's the recorder? Okay.